Okay, now it's time to start with the lecture. And in this second part of the course, we will talk about different types of sensor. So every week we will study sensors of position, in this case, for instance, speed, or sensor of temperature, force, and all the physical quantities that you can measure. As a matter of fact, what we do now is to go to the first stage of the measurement chain. Okay, so we are starting here backwards. At the beginning, you have always a sensor which converts a physical quantity, could be force, pressure, temperature. Okay, this is converted in an electric quantity, like resistance, current, voltage. Then, most likely, you have a converter. So, for instance, if you measure a current, you have a current to voltage converter. So, you enter with a current and you get a voltage. And then, once you have the voltage, typically, you digitize it, okay? And then you have the code corresponding to your measurement. We have studied how to digitize a signal. We have studied how typically we convert a resistance into a voltage, a current into a voltage, even a voltage into a voltage when, for instance, the voltage is too small and you need to amplify it before digitizing it. We have studied several methods to measure these quantities, and most typically what we do is always to convert all the electrical quantities into a voltage to be digitized, okay? We have studied how to measure a resistance, a small variation of resistance, a current, a small voltage, or, for instance, a big AC current, so we have a current transformer. We have studied all these types of measurements. Now it's time to go to the first step of the measurement chain, which is the sensor. The sensor is simply that device which transforms a physical quantity, light, temperature, pressure, force, into an electrical quantity. Okay? Today, we will talk about sensors of position. First of all, how to define a position. When I talk about position, I consider, oops, here I should use this system. No, evidently not this, but this. Yeah. When I talk about position, I mean not only linear position, it could be also circular position. So you either change an XY coordinate, but also you could change also an angular position, okay? So you could have either linear or rotational position. It could be linear or angular position, okay? It could be continuous. It means that the position can change continuously. It could assume infinite different values, but it could be also bistable, which means that we want to see if we have let's say, a digital position, which means either the object is there or not. Okay? That's also a position. That's a digital position. Let's start, and there are different physical principles which are used to measure position, and they're based on change of resistance, capacity. Sometimes they are based on optical principles or ultrasonic waves. Okay. Now let's start from the first sensor, which is a very common question of position, and it's the read contact. In this case, this sensor of position falls under the category of the bistable sensors, which tell us if an object is there or not That's what I called before a digital position. So we don't know how much the object is close to the sensor. We don't know if it's here or here. We don't know, we cannot determine the position precisely, continuously of this object, but we can only answer to the question, is the object there? Yes or no? Typically, this sensor is composed by two reeds of metal, which is ferromagnetic. So you have a tube, typically it's glass tube, so you can see the contact inside. And inside this tube, you have sealed two ferromagnetic contacts. I'm not sure if the 3D drawing I have here is clear, but these contacts are not straight, okay? So you don't have these contacts like here. Typically, they are flipped out like this, okay? So you have these contacts which are not straight like this, but bended up like this. One is bent up like this, and one bent down like this, okay? And what happens when you have a magnetic field applied to these contacts? For instance, we take a magnet and we bring it close to this sensor, okay? So here I have this magnet here, and this magnet will create a magnetic field, clearly. So you have a field which leaves the north pole and goes back to the south pole of the magnet. And on the way from the north to the south pole, the magnetic flux will meet this contact. And as I told you, these contacts are made of ferromagnetic material. What happens? Probably I've already explained to you, maybe last week, something, or 2 weeks ago, when we talked about magnetic measurements. Ferromagnetic materials are permeable to magnetic flux. It means that if you apply a magnetic field to the air, and then you have there a ferromagnetic material, the flux prefers to go through the ferromagnetic materials because it can be permeated more by the magnetic flux rather than the air. The magnetic flux doesn't like the air. It likes the ferromagnetic material. So if you apply magnetic field and the flux has to go somewhere, well, here's the ferromagnetic material, boom, let's go there, okay? You have a ferromagnetic object there, boom, the flux goes there. This is a physical property of the ferromagnetic materials, which is called permeability, which tells you if a material can be permeated by the magnetic flux. And it's typically expressed as multiples of the ferromagnetic of the permeability of the air, okay? So typically you know that you have magnetic flux density, which tells you how much flux per unit of surface you have, is given by the magnetic permeability of vacuum, which is 4 pi 10 to the minus 7 Henry per meter, times the relative permeability, which is just a coefficient which tells you how many times the permeability of the material is larger than the permeability of the vacuum, of air, times H, okay? So if you have air, the relative permeability is 1, so you have mu 0. If you have ferromagnetic materials, you have several multiples, several orders of magnitude larger permeability, okay? Now, what happens when you have these two heats, one which is here and one which is there, on the way of magnetic flux? Well, look what happens. The magnetic flux leaves the North Pole, enters in this reed, and then it has to jump again to the other reed, passing through the air. Okay? So if you take one flux line, it starts from the North Pole. It goes through the air, and it really doesn't like to go through the air. Then there is ferromagnetic material. Wow, cool. It feels comfortable. But it's just for a little moment, because then, again, it has to jump to the ferromagnetic material, and then it has to return back to the South Pole, okay? Sorry. So this is really not a convenient solution. If you watch it from the top, here you have your magnet. Then how did I draw it? Like this. Okay. So just think about this path for the ferromagnetic flux, for the magnetic flux. You leave from the North Pole, then you have all this path in the air, which is bad. That's why I use the red color. Then a very convenient path through the ferromagnetic material, then again back in the air, and back the ferromagnetic material. Well, sometimes it could go out, but most typically it will go inside here. Okay. So it could have different paths. I'm just drawing some. And back to the South Pole. Okay. So let's leave only one solution. This is most likely the way the magnetic flux will go. Okay. Now, why did I say this is not really a good path? Well, because, well, definitely the flux must go through the air here, and must go through the air here. But what about this point here in the middle? Like, why should I have this path through the air? As I told you, the magnetic flux doesn't like the air. It likes to go through ferromagnetic material. So, what happens, in fact, is that your sensor will close the contact in this way. So definitely the flux will leave the North Pole, and once it arrives to the ferromagnetic material, it will conveniently go through the reeds until coming back to the south, okay? Now, as you see, we still have this path in the north and in the south. It's not symmetric, but my drawing skills are not so good. So definitely, in order to go there, in order to go to the contacts, some flux has to go through the air. You can't do anything about that. But you can get rid about this part in the air. Because if the contacts are closed, then the flux enters here, and then it has all these paths through the ferromagnetic material. So definitely, we got rid about this part of the path in the air. Here, the flux is conveniently going through the ferromagnetic material, okay? So definitely, the flux likes more this configuration than this one. In more scientific terms, this configuration is at a lower energy than this one. Therefore, in nature, when you have a configuration at lower energy, everything works so that the system goes to the configuration at lower energy. What happens is that as soon as you have a state which has a lower energy, automatically there will be some force which will attract these two reeds, some force generated by this magnetic field, so that these contacts will close, okay? Here. So once you have this magnetic field, there is a configuration at lower energy, which is this one, where the flux feels more comfortable to stay inside the ferromagnetic material rather than going through the air, and therefore you have these forces closing the contacts, okay? And this is the result. When you bring this, the magnetic field, the magnet there, the magnetic flux closes the contacts. Before continuing this topic, it's very important to understand how the reed contact works, because I've seen somebody using this sensor in the wrong way. What they did was to have these contacts here, okay? And they use the sensor and they use the magnet this way, okay? The result was that these two materials are made of ferromagnetic material, so definitely if you put a magnet in this position, they will both be attracted by the magnet, okay? The force will be in this direction for both of them. There's no difference whatsoever because they are both ferromagnetic materials. But now, this means that when you put the magnet there, what you obtain with the contact is something like this, okay? So eventually, by moving both in the same direction, there is a point here where they touch. So they close the contact. From the external point of view, what you see is the same thing. The output of this sensor is a resistance which is either infinite when it's open or almost zero when it's closed. Okay? So the output is open, close. That's the response of our sensor. And the response is here is again open, close. Well, maybe it's not so safe here. There could be some larger resistance, but that's not the method, the working mode the sensor is supposed to work. Why? Because this is how it's supposed to work. All the values that we will see later, the working principle is supposed, they are given according to this working mode, which is the correct one. This is just a deformation of the reed sensor, which is not intended to work in that way. So it might require a larger field or, generally speaking, a closer object. And I'm not really sure how much it's going to last if you use it that way, because you have a deformation which was not designed the sensor for. Okay, so remember that even if you have a magnet and you have the reed contact there, you don't have to put the magnet in this direction, because yes, definitely they will close, but they are not closing at the same value of magnetic field that you have in this way. Okay? I know it might sound strange from the intuitive point of view because you have a magnet which points there. So you think the magnetic field points there, but the sensor is here. So if I have a magnet here, well, I should point it to the sensor, right? I want to point the magnet to the sensor. No, you have to point it parallel to the sensor so that the magnetic flux going out as a short path, a shortcut through the ferromagnetic material. Okay? If you go to any database of datasheet of reed switches, you will see that you have values which tell you at which magnetic field, well, now we should enter in this topic, it's not really magnetic field, the switch closes and open. Why I said it's not really magnetic field? Because the units is always given in ampere terms, almost always. What does it mean? It means that you have your heat contact, okay, and you wind a test coil around this heat contact sensor, okay, and you inject a current. Then you multiply the current, amperes, times the number of turns, and it gives you the magnetomotive force, which is required to operate, to close and release the sensor, okay? They are typically giving the value not in Tesla or amperes per meter. They give the ampere turns because traditionally, when they tested this sensor, simply they took a coil, calibration coil, they put the sensor inside, inject a current, and then they increase the current until they see that the sensor closes, okay? There would be a lot of discussion about these points because there is not a precise standard about how to measure these values. Keep in mind that even the heat, like the connection that you have, if they are made of ferromagnetic material, they influence the value of the switch field if you bend them in a different way because they deform the field. And that's not so simple. Really, you go into a field which is not very trivial. What is interesting to see is that this value, when you switch the read contact sensor and when you release it, they are not the same. So for instance, it might close at 10 ampere turns. So you increase the magnetic field, you have at 10 ampere turns, and it closes. But then it will release at 8 ampere turns. Why would I need this difference between the opening and closing magnetomotive force, not magnetic field? Can you try to guess it? Like, let's make an example. You can say that the switch closes at 10 ampere turns, okay? But then once it's closed, it will open at 8 ampere turns. It's not enough to go back to 10 ampere turns to open the switch, but it will go down, it requires 8 ampere turns. You have to decrease a little bit more to open the switch, which means that if you are at 9 ampere turns, well, it depends. If you are at 9 and you come from a lower value, then it means that, and the switch is not yet closed, it will be open. But after you cross 10 ampere turns and you return back to 9, after the switch is closed, it will be closed. So at 9 ampere turns, you can have two different states, either open or closed, depending on the history of where the sensor was before. Now, can you explain me why would I need such a difference? Try to reply in MS Teams. So basically, you have this behavior. As the magnetomotive force increases, it goes, it arrives to 10 ampere turns, it closes. Then it increases, it goes back. When it goes back to 10 ampere turns, does not close. It's still open. It will open later when you arrive at 8 ampere turns. Why would I need this difference? Well, it's simple. If I had a characteristic which would, once closed, that would make the sensor work this way. Once closed at 10 ampere turn, it will open back as soon as the value returns back to slightly less than 10 ampere turns. Then what happens if here I have some noise? Now I'm emphasizing, okay? Let's say that here I have some noise. Here you go over 10 ampere turns and the switch is on. But then, just a few moments later, you go below 10 ampere turns, okay? So here you go up. So here you go down, and then you go up again, okay? Actually, this is the line. So here you go to a value larger than 10 amperes turn. And it switches on. Then here it switches off because you go below, and then it switches on again, okay? This means that if you have some noise, you can randomly go to values larger than 10 and lower than 10 just in the time there is a transition around 10 ampere turns. So if you don't have this hysteresis, it will, once it once it arrives around 10 ampere turns, it will start closing and opening, like creating this this effect, and then it will be large enough to keep close. If you have some hysteresis, once it closes, okay, here it closes, then even if it goes below 10 amperes per meter, it doesn't matter because it should go below 8 to open. So it will keep closed. That's why you need the hysteresis. If it's reacting immediately and it's opening back once you go below the same value, 10 amperes per meter, which activated the sensor, then it's enough to have a small noise, a small oscillation of the magnetomotive force around 10, that once you go down, you go below that threshold after activating the sensor, it will start jumping on, off, on, off, on, off, okay? This is a technique used in many other sensors when you have the same problem. To avoid this, this effect, what you do simply is to have some hysteresis in the system, okay? So when you see the hysteresis in the system, it's typically for this reason, okay? Fine. Now, let's, I hope it's everything correct for read contacts. Why, by the way, why do you have this contact sealed? It's also because when there is a contact, never forget there could be some spark. So there could be some possibility of generating some fire if the sensor is an industrial system, in an industrial environment where there could be some gases which might be ignited by the contact, okay? How to measure position? Well, one different method is to use magnetic field generated by a magnet or a ferromagnetic component. What does it mean? Let's say that you want, for instance, to measure the number of rotation of a shaft, which is pretty common application in industrial systems because you have something which rotates, typically motors, you have shafts, and you want to measure how many rotations you have. So you want to measure the position where the position is how many times it makes a revolution. Okay, so once the magnet that you attach to the sensor is in front of your sensor, you will read the magnetic field produced by the magnet, and you know that the position of the shaft is there. Then it rotates, it goes away, so you have another position, and you get back to the same position when you get, again, the response from the magnetic sensor. So what you can do simply is to put your sensor there, you measure your magnetic field, and you can do it with very cheap sensor like Hall effect sensors or AMR. Why? Because you don't need to be very precise. You don't need to measure the magnetic field here and have a measurement with 6 digits of the value of the magnetic field. What you want to see is that the shaft rotates when the angular position of the shaft reaches the sensor. You will have a pulse of magnetic field. Then it rotates. You get another angular position. It gets back to you, and you get another pulse, and so on. Okay. If one of these pulses is larger or it's lower, you don't mind, as long as you are able to detect this pulse and see that this pulse is bigger than the big background noise, and you can clearly identify that there is a pulse. Everything you have to do is just to count a pulse, so you really don't care if it's larger or smaller. What did I mean when I talked about the noise? Just imagine that you have something like this. Can you see this pulse? Yes. You can see that it's bigger than the background noise. Here we have a level of the signal which is larger from the background noise, larger than the background noise. Can you see this pulse? Maybe, I'm not sure, but yeah, maybe we can see it. Can you see this pulse? No way. Okay. So definitely the pulse must be larger than the background noise. But once you can see it, if the pulse is this or this, you really don't care, because what you want to identify is the pulse. That's why you don't need fancy sensors of magnetic field. You can use simple Hall effect sensors, which are cheap, and they work just fine. Magnets are expensive. Well, they are not crazy expensive, but when you have to design a system and you have to care about every single crown for that system, well, definitely saving on magnets is a useful idea. So if you have to measure the position, the angular position of a system where you have a ferromagnetic material, and this material is not symmetric. So for instance, it has some grooves. It is like a mechanical system with some teeth, like in this example. Well, if it's a ferromagnetic material, definitely it has a remanence, unless you just brought it above Curie temperature. It's not demagnetized. It will have definitely some remanence. So it will have itself some magnetic field. You don't need the magnet, because simply if the sensor is closer, it's in front of this tooth, for instance, it will be sensing a field which is larger than when the sensor is facing this groove, okay? Because here it will be closer to the ferromagnetic object than when it's in front of this groove. So, of course, you cannot use this system if you have a symmetrical cylinder, because then the sensor is always exposed, is always at the same distance from the object, unless it's strongly magnetized in one particular direction. Therefore, you doesn't see any difference, okay? But when you when you have a system which has not this symmetry, you can take advantage of the fact that the magnetic field in front of this teeth will be larger than the magnetic field in front of the valley, so you can see the pulses without the need of adding an external sensor. Okay, here just plot again the same slides about Hall effect sensor, just to remind what it is. But I think that we have already talked about this sensor several times, not only for the measurement of magnetic field, but also because it was a system to multiply two signals, if you remember, because the output is proportional to the current that you inject and to the magnetic field, so you can use the magnetic field as one signal to multiply, and then the current for the second signal to multiply. We talked about it also when we had to study the quantum Hall effect, okay, which was a system to create a standard of voltage. So we have already studied this sensor several times. I will not enter into details. Let's now go to induction coil. What we have here is simple coil. For simplicity, I cut this model in half so you can see how it looks inside. So this is just half of the system. It's not the whole sensor. You have basically a coil which is wound around this pole, and then you have a magnetic yoke which surrounds it. Okay. Now, what happens when you have a magnet which moves in front of this induction coil? You probably remember that the Faradays Induction Law tells us that the voltage is proportional to negative the derivative of the flux in time. Okay. Here I forgot n, where n is the number of terms, but I mean this is, let's say this is for n equal to 1, when in fact you don't have only one term. What happens here? So you have, for instance, you want to measure the position of some object in your production line. You attach a magnet to this object, and then they will go through this production line, and then under that you have this induction coil. The magnet will bring a magnetic flux which will go through the cross-section of this area, and then this coil will feel a magnetic flux. Since the object is moving, so in this case we are measuring a position which changes in time, as the flux changes because the magnet moves, you will see a voltage in the pickup coil. Okay, so here I will have a voltage which will be proportional to the rate of change of magnetic flux due to the fact that here I have a coil, here I pass with my magnet. When it arrives here, it will induce some magnetic some flux in the coil, okay, and then it will move away, and the flux goes back to 0. So you have a peak which sees the flux increasing, the flux decreasing, and this will generate a voltage in the pickup coil. The question is, why do I need this yoke at all? I mean, the system doesn't work just with the pickup coil. The induction law doesn't require a yoke. If you think about that, our system works even if we have just a coil, right? So, where is this? Okay. So if you have your magnet, and here you have your coil, you still see a voltage due to the fact that you have a magnetic flux changing in time, right? watch it, if you make a section of this coil, you will see these turns and this flux, which changes not because the magnet is changing the value of the flux, but because the magnet goes away. Okay, so here you have your flux. If the magnet goes away, you have no flux. So here you have flux, magnet goes away, you have no flux. Which means that there is a change of flux. Okay, so why do I need a yoke at all? Why should I spend money for this yoke here that I find in the sketch of the slide? Remember, you have to spend some money for this yoke, right? And if you spend some money, it's not just to make things looking fancier. If you spend some money, it's just to make the things working better. So there must be an advantage of this yoke. Well, the advantage is very simple. In this configuration, you have only air around. So, well, the flux just behaves as the coil was not there. The flux line will go back to the from the north to the south pole, just as a normal magnet would behave in air. But what happens if I have a ferromagnetic yoke there? So let's draw it. Well, now the magnetic flux enters inside here in the ferromagnetic yoke. And then do you really think it will go out in the air to return back? No way. Why should the magnetic flux go back in the air? The magnetic flux likes to stay in the ferromagnetic material. That's permeable. That's what I said before. So instead of returning back in the air, the ferromagnetic material will behave this way. Now, let's see if I can draw it. So it enters here in the ferromagnetic material. Then it just have no reason to go back in the air. It will stay comfortably here in the ferromagnetic material and go back, okay? This is the path of the magnetic flux which has the lowest energy, because it has the shortcut through the ferromagnetic material, okay? The same also for the other flux lines. Here I have only 2 flux lines to make an example, okay? And what is the difference now? Why should this system work better? Well, if you don't have this flux, how did I call it? This yoke. If you remember, the flux was returning back this way. So only 2 turns were crossed by the flux line. Only 2 turns of the coil were able to see this flux, because it was crossing 2 cross sections of 2 turns. These turns did not see the flux, because by the time you have here, the flux is already back. Okay, so the flux was not touching these 3 turns. But if you have this yoke, the flux is brought back, is brought inside all the turns. Okay, so before going back, it will cross 1, 2, 3, 4, 5, all the single turns of the coil. In other words, using this yoke allows you to bring the flux and avoid it will go back to the magnet immediately, but you take the flux and you bring it inside the coil and then you let it go back, okay? this way, you amplify the response because all the turns will see the magnetic flux and not only the first ones on the top. Okay. What's the problem? The problem is that magnets again are expensive. So you really don't want to put one magnet on each single object you want to measure the position of. Okay, that's not really convenient unless you have really few objects. But just imagine that they are producing a lot of different objects, and you cannot attach a single magnet on every. You cannot attach a magnet on every single object. Okay, so this is an alternative. If the magnet doesn't go on the object, it will go in the sensor itself. You still need a magnet because you always need a magnetomotive force to create some flux. And in this case, we put it inside the yoke. So here we have a coil. The yoke is the same. But here we have a magnet. The magnet will generate a flux. And then what we have? A flux which arrives here. And then it has to cross the air to return to the outer ring and return back to the magnet. Okay? So the flux is generated by the magnet. It arrives here at the top of this central pillar, and then necessarily it has to go through the air to reach the outer ring and return back to the magnet. Okay. From this point of view, you can see this, it's useful to model this system with a very simple magnetic circuit. I'm not sure how many of you are familiar with magnetic circuits, but it's very simple. You can simply use the same laws that you use for electric circuits. And instead of a voltage, you have a magnetomotive force, which is given by, if you have a coil generating it, it's N times the current, N times the number of turns of the coil times the current. In this case, we have a magnet, so you have the magnetomotive force of the magnet. Then you have the reluctance. The reluctance is corresponding to the resistance in an electric circuit. Okay, the reluctance of a path where the flux flows through tells you how much that path is reluctant to have the flux flowing through that. This very same way like the resistance opposes to the flow of the electric current. Okay. Here, instead of opposing to the flow of an electric current, we oppose to the flow of a magnetic flux. So we call this property reluctance. And then you have the current. You have the flux, which is corresponding to the current. Okay. So we have the equivalent of the Ohm's law, which tells you that the flux, that is the current in an electric comparison, is given by the magnetomotive force, which is equivalent to the voltage, divided by the reluctance of the circuit, which is equivalent to the resistance. Okay, that's just Ohm's law. Current divided voltage, current equal to voltage divided by resistance. Okay, in this case, the current is the flux, the voltage is the magnetomotive force, and the reluctance is the resistance. Okay. So, if we reduce now the reluctance of the circuit, we have a bigger flux. If we increase the reluctance of the circuit, we have a lower flux. So what is the trick here? Imagine to have a surface of ferromagnetic material. Well, now the reluctance of the air decreases because the magnetic flux leaves the magnet, flows through this central pillar. Then yes, it has to go through the air, but not the entire path to the ring. It goes to the air just a little bit. Then it will have easy way through the ferromagnetic material of this metallic object that you have above the sensor. And then yes, another small path through the air. Okay? There is still some reluctance of the air, of course, here and here. But compared the previous situation, the reluctance now is smaller, because here you have the reluctance of this big path through the air. Okay? Now, the path through the air is much smaller, so the reluctance will be lower, which means that if you put a ferromagnetic object above this system, this sensor, then you reduce the reluctance of the circuit, because you reduce the space of, or the length of the, I'm saying length, but it's not really correct because it's a volume. Nevertheless, let's say the length of the circuit, the length of the path of the ferromagnetic material, of the magnetic flux in the air. It still has to go through the air, but not as much as it had before. You put there some shortcut for the ferromagnetic flux. Okay. This means that if you have now the reluctance of the air, which is smaller, you have a bigger flux, okay, according to this equivalent of the Ohm's law for the magnetic circuits. The reluctance of the yoke is the same. Typically, you can consider it negligible because they have permeability. The ferromagnetic materials have very large permeability. So just to approximate, you can just consider the reluctance of the yoke basically negligible. And you can consider only the reluctance of the air. And the reluctance of the air, in this case, is smaller because you have a smaller path through the air. Then, if you decrease the reluctance of the air, the flux increases. And then what you have? A change of flux. You have a lower flux first, then you put a ferromagnetic material above the sensor. You have a change of flux because the flux increases. And what happens when you have a change of flux? You have a voltage induced in a coil. That's the reason why you have a coil here, to pick up the change of flux given by the reduction of the reluctance of the air. Okay. There are other systems. This is not very used anymore, but for some reason, there are some people who like this sensor. This is I'm not really sure about the pronunciation of this Vigan wires. Okay. I should investigate if somebody is a native speaker of the language this gentleman was from. He can tell me what's the correct pronunciation of this name. Basically, they are composed of an asymmetry. They are composed of a ferromagnetic material which has an asymmetric behavior in the BH loop. They make some special treatment to achieve this asymmetry. So you can see that you can pick up the change of ferromagnetic flux with different pulses, positive and negative pulses with different amplitude, according to if you are going to positive or negative direction, which means saturation from negative to positive saturation. So you have a steeper change, so bigger pulse, and in the opposite direction, you have a negative transition, which is in fact smaller. It has a slower rate of change of flux and therefore a smaller pulse. Just to be clear, here S and J doesn't. It's just there from Czech. S means sever, which means north, and J means E, which means south. Okay, so just north-south. The labels there are still in Czech. Now, in the last 15 minutes, probably I can talk about eddy current sensors. Again, in this case, we want to identify the position of an object, and specifically a conductive object. Not necessarily ferromagnetic material. It can be any conductive object, conductive of electric current, of course. These are basically what they use, for instance, at the disco to check with this metal detector, to check if you have some knife in your pockets, to see, or also the airport, to see if you have some metallic object with you in a security gate. These devices are based on, or maybe, well, one more interesting application is, for instance, to detect anti-personal minds. You know that unfortunately when humans make war, they have this bad habit to put in the field anti-personal mines. So you have some mines which are activated when somebody steps on them, and then they mutilate the people when they don't kill them. And typically the mines have some explosive in some plastic shape, in some plastic container. And they need, however, some device to activate the explosive. And they try to put as less conductive material as possible, but there is always some little part which must be metallic to make the mine work, and therefore it's conductive. So the only way you can detect them is basically to search in the ground for conductive materials. Okay? When you know that in some area they installed anti-personnel mines, you go with this metal detector and you search for this tiny fraction of conductive material in the anti-personnel mine. These sensors are based on two basic principles that we already know. If you have a coil and you inject a current, then you generate a magnetic field. Okay? This shouldn't surprise you. Now, if you have a coil, your solenoid, you inject a current, you generate a magnetic field. You generate AC or DC magnetic field. Doesn't matter. DC current generates DC magnetic field. If you have an AC current, you generate an AC magnetic field. The second effect is backwards. If you have a magnetic field with changes inside the coil, you will generate a voltage at the terminations of the coil. It's again a principle that we have studied extensively in this course. In this case, be careful, because if you have a DC magnetic field, this will not generate anything, but this law applies also only if you have an AC magnetic field, because AC magnetic field will change in time, and therefore it will have a derivative, and we know very well that a derivative of the magnetic flux in a coil will generate a voltage. That's the reason why I wrote here B, flux density, and here I wrote B of T, which must to highlight that this flux density should change in time. Okay. How do we use these two principles to identify the position of a conductive object? Well, let's take a cross section. Okay, so here we cut our coil on this line, and we watch what happens. We inject a current in this coil, and this coil will generate magnetic field. Okay, that's what we are doing here. Inject a current, and you will generate a magnetic field. That's what we have here. Then let's imagine we have this portion here of this section of a conductive material. Now, I will ask to make this this idealization. Just think that this object of conductive material you want to measure the position of will be composed of concentrical coil. Okay? Of course, it's not composed of concentrical coil. It's just a way to imagine this object. Okay? Let's say that you have a disk of copper, for instance. Copper is a conductive material. And it's solid copper. It's just a disk of copper. So we take the section here. We watch the section. And instead of having a solid copper disk, we can imagine this this composed of, like if this is the axis, so this is the central axis, you can imagine this disk of copper composed of a ring with this diameter, okay? Plus a ring with this diameter. And so on, okay? So you can imagine that instead of having a ring, a solid ring, you have the ring sliced in different, so instead of having a disk, I confused the words. Instead of having a disk, solid disk, you have several rings with different diameter, which altogether compose this solid disk, okay? For instance, you have this ring. Now, what happens to this ring? Or to this ring, for instance? Well, you have some magnetic flux which goes through this ring. So just imagine that you have a ring and you have the magnetic flux which enters the ring. Okay? And this is a ring composed of conductive material. So you can imagine it as if it was a coil with one turn. You have a ring, you have the flux which enters the ring. So if you like, you have only one turn and some magnetic flux which goes through that. What does it mean? It means that in that ring, you will have some current. Why? Because you have a magnetic flux which enters in the ring. It changes in time. Because what probably I didn't mention is that you will have this magnetic field which changes in time, okay? So with the first coil above here, you generate a magnetic field which changes in time. This flux will enter in this ideal ring. Doesn't exist again. It's just a way we can see the solid disk here. It will change in time, and it will generate some voltage. But in this case, this one turn coil symbolized by the ring is a closed coil. So you have a voltage generated on this coil, which generate a current. So a current will circulate. Just imagine that you have a coil. You know that when some magnetic field changes in time and enters in the coil, it will induce some voltage. And if you close the coil, you will generate some current, which, by the way, will try to create a magnetic field opposed to the field which created that current, okay? The same here. You have this disk. You can see the disk as a series of concentrical ring. Then you have some magnetic flux which enters, generated by the first coil, okay? So you inject a current here. You will generate some magnetic flux. The magnetic flux changes in time, and therefore it will generate some current which circulate in this ring, okay? A current which then it will generate a back field B, okay? Because you have a current which circulates in a ring. Now, I did it only for one ring, but just imagine that this happens for all the ideal rings that we have here in these schematics. Those rings that we said they compose the whole disk of the object. Okay. So now you will have a current which flows in this ring, another value of current in the outer one, another out, and another current inside, okay? So you have in the disk, if you watch it like this, you have all these currents which generated by the magnetic field caused by the first coil. These are called eddy currents, okay? Fine. So I said, you have a current which flows in this ring, in this ideal ring, and what we know? We know that if you have a current circulating here, it will generate a back field, which, generally speaking, is balancing the field which created that current, okay? That's the reason why you have a negative in the sign of the equation of the induction law. If you don't have that negative, the field, this current would create a field increasing back the same current, and you create free energy, which doesn't exist, unfortunately. So you have a magnetic field here. It will generate an eddy current, and the eddy current opposes the magnetic field which created the eddy current itself, okay? Now, let's observe the field created by the current, the eddy current flowing in the copper disk. Now we put two coils above this object, one close and one far away. The coil which is close to the object will feel a larger field. Why? Because more flux lines crosses its cross-section, okay? So here you have 1, 2, 3, 4, 5, 6 flux lines going through this coil. By the time you arrive at this distance, well, you have only two flux lines crossing this coil. So it feels a lower magnetic field because it's more distant, clearly. Now we put all the pieces together. You have the first coil in the middle, which will generate a magnetic field. The magnetic field will be equal for the receiving coil on the top and for the receiving coil on the bottom. This magnetic field will generate an eddy current in the conductive object, and the conductive object will generate a field which now is not the same for the receiving coil on the top and for the receiving coil on the bottom. Now, the receiving coil on the top will feel a lower field than the receiving coil on the bottom. Here, the field generated by the first coil is identical for the top and for the bottom. The back field from the conductive object is bigger for the bottom coil than for the top coil. Therefore, if you watch the flux generated, the flux in the top coil, you have the field Bg, which corresponds to the field generated by this coil, plus the back field low. In the bottom, at the bottom coil, you have the Bg field generated by the first coil, plus the back field from the metallic object, which is high. Then, once you take the difference between these two coils, of course, they will generate a voltage because the flux is changing in time. The voltage is proportional to the flux. The frequency is the same. So you will have a voltage which is proportional to the flux. So if here you have a magnetic field which is larger than here, once you take the difference of these two voltages, you get rid of the component of the voltage generated by the field of the first coil. Bg and Bg go away, and then you get only with the difference of these two magnetic fields. Okay? Again, when you take the difference of the voltage induced in the top coil and the bottom coil, they are the same. So this magnetic field eliminates each other. Okay, you don't have it anymore because the magnetic field here is equal to the magnetic field here. They are at the same distance. But then, so once you take the difference, you get rid of that component, which is equal, and you watch only the difference between the magnetic field here and here. So what this means is that what you see is only the presence of a metallic object, which, if it's close enough to the sensor, will generate a magnetic field large here and low here, thanks to the eddy currents flowing in the object. And therefore, you can see that the voltage will be larger than 0 because we don't have symmetry in the system anymore. If you have no object here, you have only these fields reaching the secondary coils, top and bottom, which are the same, so the difference will be 0. If you have some object, some metallic object, in the close enough to the sensor, it will have some eddy currents, and therefore it will create some asymmetry in the field. Here you have a larger field than here, and once you take the difference, you see that you have some signal. Of course? Okay? Fine. Here is what you do. So you have a first coil, which generates a magnetic field. Here you have the eddy current, and then you have the back field, which is bigger here than here, and you take the difference of these two coils. So you have a coil here, and then here in anti-series, you see. You enter from here, you have clockwise, then you go up, and you have counterclockwise. So they are in anti-series. Of course, the trick here to make a good sensor is to have very precise alignment of the distance between, or very precise distance of the central coil to the receiving coils, because as soon as this coil is not perfectly in the middle, then it will induce a coil, magnetic field bigger here than here, if it's closer to this coil than this here. So the trick when you want to make good sensors like this is always to have a very precise positioning of your coil, so that it's really in the center, and it will really, this generating coil, be giving the same flux on the top and the bottom coil. Now, I think I'm already 1 minute over my time. So if there is any question, this is the time to do it. Otherwise, we can meet each other tomorrow morning, okay?